All right, William, can you hear me okay?
Yeah, we can hear you.
Great. All right, so let's get rolling. Hello, good morning, everybody. I hope you're having an excellent day. Today we are just continuing our work in chapter 4. So last time we were looking at critical points, local maxes and local mins. And as a reminder, there's going to be a review session today from 5 to 6 with William, where he's going to do some more practice problems on that. So if you think you'd like more practice, the link is in Moodle. You can also refer to the asynchronous videos on 4.1 if you're looking to see some more problems done out. So today we are going to be doing 4.2 inflection points, and then we will likely start a little bit of next week's work today because we'll have a little extra time since we don't have class next week on Thursday for Veterans Day. So we're going to try to get a little bit ahead. So we'll do some profit cost type examples and applications to the work we've been doing on Tuesday and today. So the work we're going to be doing today is called inflection points, and we've talked about inflection points before back in chapter 2, and now we're going to sort of formalize these a little bit. So let me switch over to the dot cam. Okay. So last time we were talking about local maxes and local mins, and that all had to do with the first derivative. We were looking for critical points, which is where the first derivative equals 0. And then we looked at how we can use different types of information to classify our critical points. Inflection points have to do with the second derivative. So now we're sort of moving on to the next derivative. And as a reminder, an inflection point is a point on a function where the function changes concavity. So it can either change from concave up to concave down or concave down to concave up. So looking at this picture right here, the inflection point is going to be right around here, right? And we can see that to the left of the inflection point, we are concave up. And to the right of the inflection point, we are concave down, right? So we're looking for roughly where we change. And so there's some interesting things that we need to remember about concavity and the second derivative and how we relate it. So as a reminder, when you are concave up, right, which we are to the left of our inflection point, then your second derivative is going to be positive whenever you are concave up, right? So here, you're concave up. And then whenever you are concave down, which we are over here, your second derivative is going to be negative. And this is going to be important in a few minutes, and you'll see why. So right at our inflection point, right where we change concavity, that is exactly the spot where our second derivative is equal to 0. In order for the second derivative to change signs from positive to negative, or if it was negative to positive, it would have to go through 0. So this is a really important piece of information, that when you have an inflection point, the second derivative equals 0. However, that statement only goes in one direction, right? So if you have that the second derivative equals 0, it doesn't necessarily mean that it's an inflection point. It could be a weird spot. So we have a second sort of qualifier to make sure that's an inflection point. And that qualifier is that if your second derivative equals 0, you also need the second derivative to change signs around your inflection point, right, in the second derivative, because that guarantees that we are changing concavity. Okay, so what does that mean? What do we do with it? How does this all work, right? So we want to be able to identify these inflection points on an original function. And we're going to figure out how we can do this algebraically and analytically as we sort of go along. So let's start with an example and see what this process might look like. So consider the function f of x equals 2x cubed minus 3x squared minus 36x plus 14. We want to find the inflection points of this function. So we do start by using the fact that we want to know where the second derivative equals 0. Okay, so we start with the first derivative so that we can get to the second derivative. So the first derivative for this function will be 6x squared minus 6x minus 36. And now the second derivative will be 12x minus 6. So what we do is we find the second derivative and we set it equal to 0. And we're going to solve for x. So 12x equals 6, or x equals 1/2. So if we have an inflection point, then we will find a potential place for it when the second derivative equals 0. However, what we need to do is we need to make sure that we check if it's actually an inflection point. So once we get any candidates for an inflection point, what we're going to do is similar to the first derivative test that we were talking about last time. We're going to create a number line on the second derivative, and we're going to put all our possible inflection points. So here there's only one, so that makes it a little bit less arduous, less steps, right? So there's one inflection point, we put it on our number line, and what we want to do is we want to test something a little bit to the left and a little bit to the right to make sure that the second derivative changes signs. Because if it changes signs, the original function changes concavity. So much like when we did the first derivative test, we want to pick our test points to be easy to work with. So when I pick something to the left of half, I think I'm just going to pick 0, right? 0 is a little bit to the left of half. If I plug a 0 into my second derivative, I have 12 times 0, which is 0, minus 6 gives me negative 6. So the 6 doesn't really matter. What matters is the sign. I know it's negative here. I also want to pick something to the right. So I'm going to pick a test value of 1, just because it's easy to work with. 12 times 1 is 12. 12 minus 6 is positive 6. Okay, so here I can see that I've changed signs. And so that's important because, again, if the second derivative is negative, you're concave down. And if it's positive, you're concave up. And so what's happening is I'm changing concavity, which is the definition of inflection point. So x equals half is indeed an inflection point because the sign changes around the point. And again, it doesn't matter how it changes. It could go from positive to negative or negative to positive. What matters is that it does change around the inflection point. Okay, so that's how we are going to approach inflection points algebraically. We are going to look for where the second derivative equals 0, and then we are going to test in between on our intervals just to see that the sign changes. If it doesn't change, then it is not an inflection point. Okay, so let's try one here. Okay, so consider the function 3x to the 4th minus 4x cubed plus 6. I want you to find the inflection points of this function. So you'll find the first derivative, then the second derivative, set the second derivative equal to 0. Then any possible inflection points, you're going to chart on a number line, and you're going to test the intervals to see if we change signs around possible inflection points. Okay, so take about 2 minutes, see what you can work out, try it out, and then we'll go through it together. take about 30 more seconds. All right. So again, we want to start by finding the first derivative. I'm just going to do the first derivative above because we're not going to use it for anything other than finding the second derivative. So the first derivative here, I get 12x cubed minus 12x squared, and the 6 goes away because it's a constant. Now I can use that to find the second derivative. So I have 36x squared minus 24x. And so I start off by asking, where does this equal 0? Well, what I notice is that both the terms have x's in them, and it looks like they both are multiplied by 12. So I'm going to factor this to find the roots. You don't have to do that. It's just a matter of preference. So here I'm going to pull out a 12x. And so from the first term, I'm left with a 3x. And from the second term, I'm left with a 2. By factoring, this helps me visualize where the zeros are. You can use things like the quadratic equation or other algebra tricks that you know that's totally fine. So the first factor gives me x equals 0, because if x equals 0, the whole thing will be 0. And then the second factor is going to give me x equals 2/3. So the two possible places I have inflection points are at 0 and 2/3. So now I'm going to go ahead and chart these. Second derivative, so I'm going to put them in order, so 0 and then 2/3. So again, I have to test some points to the left of 0 and between 0 and 2/3 and to the right of 2/3. I get to pick the points, and I'm again going to pick them to try to be convenient for testing. So I do want to point out that, like when we did the first derivative test, you can also just sort of think about the factors and whether or not things are going to be positive or negative. So for example, at -1, 12 times -1 is negative. And then 3 times -1 is -3 minus 2. That's negative. Negative times negative is positive. So you can do it that way. You can also just plug -1 into the second derivative on like a calculator if you're more comfortable doing that. That'll give you 36 plus 24, which is going to give you 60. So you'll still get a positive number. Either method is totally fine. Here, I'm going to pick the value 1/3 to test, because 1/3 is right between 0 and 2/3. So 1/3 times 12 is positive. 1/3 of 3 is 1 minus 2 is negative. Positive times negative, negative. And then I can pick something to the right of 2/3, like 1. 12 times 1 is positive. 3 times 1 minus 2 is also positive. Positive times positive is positive. So what I see here is that around 0, I change from positive to negative. So I change signs. So that is an inflection point. And then I see around 2/3, I go from negative to positive. So that is also an inflection point. Okay. I will tell you that in reality, when you do these types of problems, about 85% of the time, the values that you solve for are actually inflection points. So that happens more often than not. But about 10 to 15% of the time, there's one that sneaks in there because of the function, whatever's going on, that there's a weird spot, and there's one that's not an inflection point. So you do have to test every time just to make sure that it's actually an inflection point. Okay. So the next way this comes up is probably not going to be surprising. And this is sort of the most common way we see these types of problems for inflection points, in that it's sort of lumped in with a local max min type of question. So this is, like I said, sort of the very common chapter 4 question. Find all local maximums, minimums, and inflection points for the function. So we know that we have to find the first derivative for critical points. We know we have to find the second derivative for inflection points. And so I will tell you that my recommendation for you when you try this problem is that you use the second derivative test to classify your critical points, since you have to find the second derivative anyway. You don't have to. You can use the first derivative test if you like that better. You can use the original function. You can try to graph it. But since you're going to have the second derivative for inflection points, you can also use that for the second derivative test. So I'm going to give you about 3 minutes for this one. Think back to what we did on Tuesday about finding critical points to help us find the local maxes and mins, and then the second derivative to tie in the work we're doing today to find inflection points. Okay, so take about 3 minutes and then we'll go through it together. All right, take about 30 more seconds. All right, so for local maxes and mins, we're going to start off with the first derivative and find our critical points. So our first derivative here, we're going to have 6x squared plus 6x minus 180. Okay, so I'm going to factor this. I prefer factoring, but again, if you prefer the quadratic equation, that's totally fine. So when I factor this down, I'm going to get 6 times x plus 6, x minus 5. Okay, and so I did that by pulling out a 6, leaving me with x squared plus x minus 30. Two numbers that multiply to give me negative 30, but add up to give me positive 1, gives me this. So my factors here are x equals negative 6 and x equals 5. So those are my critical points. Okay, so I use the first derivative to find my critical points, and then I have to do a test for those critical points to determine what they are. And we talked about how there's a whole bunch of different tests we can use, but one of them is the second derivative test. And so since I have to get the second derivative anyway for inflection points, I'm going to use the second derivative test, but if you used a different test, that's fine. So my second derivative here is 12x plus 6. Okay, So for the second derivative test, what I'm doing is I'm plugging each of my critical points into the second derivative to determine the sign. So if I plug in a -6, I'm going to get -6 times 12, which is -72, plus 6 is going to give me -66. So what matters is that I get something that is negative, right? So if your second derivative is negative, the original function is concave down, which means your critical point is a local max. I also want to test my other critical point of 5. So 5 times 12 is 60, plus 6 is positive 66. If your second derivative is positive, the original function's concave up, and you get a local minimum. Okay, so now I've used the second derivative to classify my critical points, but I'm also going to use my second derivative to look for inflection points. So I need to set my second derivative equal to 0. So I subtract 6 over and then divide by 12, and I get x equals -1/2. So if I have an inflection point, this is where it will be, but I need to check. So I throw that -1/2 on a number line. I want to test something to the left and something to the right. So when I test something to the left, I'm going to use -1. And when I test something to the right, I'm going to use 0, just because they're convenient for me. So if I take 0 and I plug it into the second derivative, I get 0 plus 6, which is +6. So that's positive. If I put -1 into my second derivative, I get -12 plus 6, which is -6. So that is negative. So I see that I change signs around -1/2. So this is indeed an inflection point. Okay, so on a mini quiz or on a chapter quiz or things like that, if you have this particular problem, you'd be looking for an answer that said the function has a local max at x equals -6, a local minimum at x equals 5, and an inflection point at x equals -1/2, right? Because those were the 3 things that we are finding. So those would be listed together in one answer. Okay, so this is a pretty common, like I said, question to try to work through. I wouldn't be surprised if this shows up on your chapter 4 quiz in some way, because this is sort of a typical problem. All right, so hopefully putting all those things together is starting to feel like it makes sense based on what we were doing last time. Now we're going to look at some other applications of how we might use information about inflection points and critical points to answer other types of problems. Okay, so these are sort of the more algebraic problems. So the next problem here is we want to find a formula for a cubic polynomial, ax cubed plus bx squared plus cx plus d, that has a critical point at x equals 4 and an inflection point at 2, 5, and a leading coefficient of 1. So what we are trying to do in this problem is figure out what A, B, C, and D are that satisfy these conditions. Okay, so let's talk for a few minutes before I let you start this on what we know. So a leading coefficient of 1. So the leading coefficient is the number in front of the term with the highest power. So that's x cubed. So what this is telling me is that A equals 1. Okay, so that means I can already rewrite my function as x cubed plus bx squared plus cx plus d, because I know that A equals 1. Okay, so what are we going to be doing here? Well, I'm going to advise you that you want to start by finding the first derivative and the second derivative in terms of these values here, where B, C, and D are just numbers. Okay, then once you have your 2 derivatives, we are going to be using the fact that we have a critical point at 4. So if we have a critical point, that means the first derivative will be 0 at 4. So f prime of 4 equals 0. That's what this piece right here is telling me, a critical point at x equals 4. We also know that we have an inflection point at 2, 5. Now 2, 5 is the location on the original function. What I can take from that, however, is that the second derivative at the x value at x equals 2 has to be 0. Because if you know there's an inflection point there, then that tells you the second derivative has to be 0, right? Not the other way around. So these are the two pieces of information that we have from this setup. So I'm going to go ahead and let you go. So find the first derivative and second derivative. See if you can use this to find B, C, or D, and then see what you need to do to find the other ones. I will also highlight that 2, 5 is a point on the original function. Okay, so you may need that later. Okay, so take about 2 minutes, see what you can figure out, right? See what you can put together. It's kind of like a big puzzle, and then we'll go through it together. All right, take about 30 more seconds. All right. So as I mentioned, it's going to be helpful if we start by finding the first and second derivatives here. So the derivative of x cubed will give us 3x squared plus, now here the 2 will come down and we'll have 2bx, and the derivative of cx is c, and the derivative of d is 0. And the second derivative then becomes 6x plus 2b, okay? So hopefully these derivatives are becoming more and more familiar to you through the work that we did in chapter 3 and now practicing them in different contexts. So here, what I notice is that my first derivative has 2 unknowns, b and c, but my second derivative only has 1 unknown, just b. So I'm going to start with my second derivative because that's going to be easier to work with. So here, I remember that the second derivative at 2 has to be equal to 0. Again, because I know that I have an inflection point when x equals 2. So if I were to plug that in, so f double prime of 2, I'm going to get 6 times 2 plus 2b has to equal 0. So now I can solve for b. So I have 12 plus 2b equals 0. If I bring the 12 over and then divide by 2, that's going to give me that b equals -6. So because there was only 1 unknown, starting there was really helpful. So I'm going to add this to my list. B equals -6. I can also plug that into the first derivative for my value of b. So if I do that, my first derivative now becomes 3x squared. Now, if b is -6, -6 times 2 is -12. So I have -12x plus c. Now that I've plugged b in, I only have 1 unknown. So if I go back to this list where I know something about the critical point, so the critical point is at 4, so the derivative will have to be 0 when x equals 4. So here, I plug in a 4. So I have 3 times 4 squared minus 12 times 4 plus c. So 4 squared is 16 times 3 is 48. So I get 48 minus 48 plus c. And I know that that has to equal 0 because when x is 4, y is 0. So 48's cancel and I get c equals 0. Okay, so now I have a value for a, I have a value for b, and I have a value for c. So the last piece I need is some sort of value for d, right? So let's put together what we have so far, right, into our equation. I think that'll be helpful. So if a is 1, I have x cubed. Now b, we have -6 x squared. C is 0, so that whole term goes away, plus d, right? So this is what I know so far. And now I need to solve for d. So this is where this point comes in. This point is on the original function, which means that when x equals 2, y equals 5. So here, what I can do is I can plug in a 5 as my dependent value. 2 cubed minus 6 times 2 squared plus d. So here I have 8 minus 24 plus d. So 8 minus 24, I get -16 plus d. I add the 16 over, and I get d equals 21. So now I have the value for a, for b, for c, and for d. So now I can put together my final answer for this cubic polynomial, which is 1x cubed minus 6x squared, 0x plus 21. So this is the function that satisfies all of these constraints. So what were the key things here? The key things here are really these two things on the right, that the derivative at 4 will have to equal 0. That's what we're using for our critical point knowledge. And that the second derivative at 2 would have to be 0 because of what we know about inflection points. The rest turns into a big algebra problem, And so we have to be really careful as we're doing all the different steps, because algebra can be tricky sometimes to solve for the rest of the variables. Okay, so that one was a little tricky, but hopefully now that we've gone through it, you sort of see the important connections we're supposed to be making. So let's look at another example here. This one actually spans 2 pages. I don't know why I printed that way, but let's just read the question and then we'll think about what we're looking for here. So suppose we have the following information regarding the first and second derivatives of a function. So this type of chart is what we were doing for like the first and second derivative test, right? Where we know where the first derivative equals 0 at 0 and 2, and then we know the sign of the first derivative for the different quadrants. And then for the second derivative, we know where the second derivative equals 0 and the sign of the second derivative in the different quadrants based on where that was 0. So what we're trying to do in this particular problem is find any critical points and bonus points if you can figure out if it's a local max or a min, and finding any inflection points. Those are the 2 questions. They're on the next page, but I'm just going to say them. So what I want you to do is find critical points and find inflection points based on this information. Okay, and again, if you are able to determine if they are local maxes and mins, you get extra fake bonus points. Right, because we could certainly ask that even though we didn't in this particular problem. So take 1 to 2 minutes, look at the information you have, think about how to sort it out based on what we know, and see if you can figure out where these things exist. And then we'll go through it together. All right, take about 30 more seconds. All right, so let's start with critical points. So we know critical points happen when the first derivative equals 0. Okay, so if we're looking at this chart, I see y prime equals 0 in 2 places. So I need to figure out what associated value goes with those. So it looks like that happens at x equals 0. And again, at x equals 2. Those are the 2 places in line with where it says the first derivative equals 0. So x equals 0 and x equals 2. Now, if I'm thinking about what type of critical point these may be, I need to look at how the first derivative changes sign or doesn't change sign around the point. So let's start with 2. To the left of 2, the derivative is positive. And to the right of 2, the derivative is negative. So if we go from positive to negative, that tells me that 2 is a local max. Okay, now looking at 0, to the left of 0, my first derivative is positive. To the right of 0, my first derivative is positive. So I didn't change signs here. So that tells me that 0 is neither. It's not a local max or a local min. Okay. So now let's talk about inflection points. So we start off by looking at where the second derivative would be equal to 0. So that's down on the second chart. I see two places where this happens. It happens at 1 and it happens at 0. Okay, so if x equals 0, x equals 1, but I need to make sure that these are inflection points. So I look at the sign of the second derivative to see what's going on here. So to the left of 0, I see that the second derivative is negative. To the right of 0, I see that it's positive. So to the left of 1, it's also positive. That's the same interval. And then to the right of 1, I see that it's negative. So for both 0 and 1, I change signs around the second derivative. So they are both indeed inflection points. Okay, so here is just, an example of a chart that gives you information about both the first and second derivative. And we just want to make sure that we know how to interpret that information. Okay, so let's go on to the next problem here. So for number 6, it says, suppose that f prime of x is given in the graph below. So I want to very clearly label the information we have. Use this graph to determine inflection points for f of x on the given interval. So I want to point out that we are looking for inflection points of the original function, not of the derivative. We are trying to use the derivative to help us understand something about the original function. So the question is, how can we use the first derivative to help us understand information about the second derivative? And we talked about these relationships back in chapter 2. So I want you to think about how we might use the first derivative to think about the sign of the second derivative, and then what we know about inflection points in relation to the second derivative, and put that all together to make a good educated guess about where the inflection points of the original function may be. Okay, so I'm going to give you 2 minutes. Think it through. If you have notes with you from chapter 2, feel free to look back, see what you can figure out and what you can remember about how we analyze these types of graphs. Okay, so I'll give you 2 minutes and then we'll go through it together. All right, so let's go through this. This is sort of a reach back, so we're connecting back to what we were doing before. So you may or may not remember sort of the nuance of what the first derivative tells us about the second derivative. But before we get to that, I want to remind you that inflection points on the original function, we should be thinking, where does the second derivative equal 0, right? That's what we're interested in. That's sort of our first step when we're talking about inflection points. So now we're thinking, okay, how do we talk about the second derivative based on what we know about the first derivative? So I'm going to remind you of some of the rules that we had, where if the first derivative is decreasing, so here, that's where the second derivative will be negative. That also is going to happen over here. So decreasing, second derivative is negative. And when the first derivative is increasing, that's where our second derivative is positive. And where we change from increasing to decreasing is where the second derivative equals 0. Right? That's where we have horizontal tangent lines, and that's usually where we started our graphing. So the three places where the second derivative equals 0, we can get by finding these horizontal tangent lines. So this looks like x equals 1.5. Oh no, we'll call this x equals 4.75. It doesn't have to be exact. This is, x equals negative 1.5, something like that. Okay. And remember, we're always asking, is it actually an inflection point? Well, we know it is because our second derivative is changing signs around our inflection point, right? It was it was negative to the left of this one and positive to the right, right? So that makes it inflection point. For this inflection point, we were positive to the left, negative to the right. And over here, we were negative to the right, positive to the left. We can see that changed because we were changing from increasing to decreasing. So now we're sort of going back to those rules. And when we first learned them, I said these are going to come back. And this is where they first start coming back, where we're using information that we know about the first derivative and how we go from the first to the second derivative to now talk about things like inflection points. So again, what did we look for here? We're interested in where the first derivative equals 0, because or where the first derivative has a horizontal tangent line, I should say, because that's where the second derivative equals 0. But we're also interested in where the first derivative is increasing and decreasing to ensure that we actually change signs in the second derivative. Okay. So we're going to use the same type of analysis, right? These rules that we're just talking about now, but now we're going to do this for a table. Okay, so suppose that f of x is a continuous function. Given the table of values for the first derivative, determine the most likely places or place that f of x would have an inflection point. Okay, so it's printed on the next page. But the idea here is that we have a derivative set of values here. So negative 14, negative 8, negative 4, 0, 5, 2, negative 1. So we need to think about what we just talked about in terms of how do we know when the second derivative is positive? How do we know when it's negative? Where might it change in relation to increasing, decreasing of these types of values? So I want you to take a minute, sketch out what you can to think about like what these relationships might look like, and then we'll go through it together for the table. All right, let's just take a look at this. Let's see what we can figure out. So if we want to talk about the second derivative here, since we're looking for inflection points, we want to consider where the first derivative is increasing and decreasing. So starting here, negative 14 to negative 8, that's increasing because I'm becoming less negative. Negative 8 to negative 4 is increasing. Negative 4 to 0 is increasing. 0 to 5 is increasing. And then I stop. So here, f prime of x is increasing. And that tells me that the second derivative is positive from x equals 0 to x equals 8. But then I have 5, 2, -1. Those values are going down. So here, the first derivative is decreasing, which tells me that the second derivative is negative. Now, what I need to remember is that in order for my second derivative to change from positive to negative, it's going to have to go through a 0, right? And so where we change from positive to negative or negative to positive is the likely spot for our inflection point. And for this particular problem, that happened at x equals 8. So at x equals 8, I changed signs based on the information I have. And so that is where I have my likely inflection point. And I want to take this moment to remind you that when we do this type of work on a table, we are giving our best guess based on the information that we have, right? So the inflection point might be at 7.7. It might be at 8.9. I don't know, but we only have information at 0, 2, 4, 6, 8, 10, and 12. So our best guess is that it happens at 8, right? We know it's going to happen near 8, but our best guess based on this is 8. So with tables and data, it's almost always a best guess and not an absolute, okay? So that's how we would look at that on a table. So lots of information about inflection points, how we find them, how we analyze them, how we can use the first derivative to talk about them. And this will keep coming up, but we're going to shift gears now, and we're going to look at an application of, well, we'll probably only get through maxes and mins today, and how we start to use maxes and mins and inflection points in different ways. So we're going to look at a couple of applications of how this might come up in business and economics. Next week, we'll finish the business economics, but we'll also eventually look at this in biology and in chemistry as well, because what we're trying to do now is take this idea of maxes, mins, inflection points, and see how they sort of show up in the real world. Okay, so as we think about these in context, I want to remind you about the definitions we have and what we know so far. Okay, so we're talking about profit, revenue, and cost when we talk about business and or economics. And so your cost function is the amount of money it takes from your own selling perspective to make a product. So if you're making bowls, you're thinking about all the costs that are associated with making and selling bowls, right? And so there's a couple of like tangential definitions we have. So the fixed cost, C of 0, is the cost before you've produced any items. So fixed costs are also sometimes called upfront costs. They are not based on how many items you're making, but are more of an initial investment. So if you're making ceramic bowls, maybe you buy a kiln for your studio, right? Which is the big oven that they get fired in. You only pay for that once, right? And you haven't even made any bowls yet. So that would be a fixed cost, for example. We also have revenue. So revenue is the amount of money that you take in from selling your product. So the way we structure this formula is price times quantity, where the price is what you are selling it for, and Q is the quantity, the number of items you sell. So P is a constant in this formula, and Q is the variable. And then profit, sort of the tie-in of these two, is the amount of money you make by producing and selling an item. So you take your revenue, which is all the money you got from selling your item, and so you subtract off the cost, which is how much it costs you to make the item, and that gives you your profit. Okay, so that was back from chapter 1. And then in chapter 2, we also talked about marginal cost, which is the derivative of cost. So that'll be the additional cost to make one more of whatever you're making. Marginal revenue is the additional revenue you take from selling one more of your item. And the marginal profit is the additional profit you take in from making and selling one more item. So the difference between marginal revenue and marginal cost. So that was from chapter 2. So now we want to take all that information and tie in what we're learning about maxes and mins. So for example 1, I'm going to have you try this one. I want you to think really carefully about the wording. For parts A, B, and C, you're only using the information that we had before. We're not bringing in anything new at this point. We're just trying to remember how to do this. For D and E, this is where we're bringing in this idea of critical points and the first derivative, and setting up things for local maxes and mins. So I'm going to just read the functions in case you can't see them, but I want you to try this because I really want you to pay particular attention to the wording of each question to really understand what they're asking for. And so just the setup says, suppose that the cost to produce an item is given by C of Q equals 10Q squared plus 1400, and the revenue is given by R of Q equals 4,400 times Q. Okay, so for part A, how much does it cost to make 15 items? B, how much does each item cost when they are for sale? So think about that wording. C, what is the profit function for this model? So you're setting up the profit function based on original definition. And then D, this is where our local max min stuff comes in. What is the quantity that maximizes profit? So we're thinking critical points, we're thinking, testing the critical points to see what's a maximum. And then part E says, what is the maximum profit that can be achieved? So I want you to think really carefully about the difference between these two questions and what we're actually looking for. Okay, so I'm going to give you about 3 minutes to try to work these out, see what you can come up with, and then we'll go through it together. All right, take about 30 more seconds. All right, so part A, how much does it cost to make 15 items? So here we're talking about just the cost function. We're just trying to figure out how much is it going to cost us to make these 15 items. So we're going to plug a 15 in wherever we see a Q. Okay, so we're going to crunch that number on a calculator. We get 3,650. And as a reminder, when we talk about cost and revenue, we're talking about dollars, right? So we're talking about money. So $3,650 is how much it costs us to make 15 items. For part B, it says, how much does each item cost when they are for sale? This is a weirdly worded question, which is why I want to talk about it. So how much does each item cost when they are for sale? This actually doesn't have anything to do with the cost function. This is asking about the price. So what is the price when you are selling them? So that's how much it costs for the buyer, which translates into the price. So remember that the price comes from the revenue function. So revenue is price times quantity. So we go to the revenue function and we see the constant that's there, and that's $4,400. Okay, so that's how much they cost when we're selling them to another person. That is the price. It's a little weirdly worded. Part C, what is the profit function for this model? So I want to remind you that profit from before is revenue minus cost. So we need to take our revenue function, 4,400Q, and subtract off our cost function. And I want to remind you that since cost has two terms, we need to use parentheses. So 10Q squared plus 1,400. Okay. So setting up the profit function is important for us for parts D and E, because that's what we're going to be working off of. But we were able to set up profit functions from what we did before. Okay. So now is where we get into sort of this maximization. What is the quantity? So we're looking for a Q that maximizes profit. Okay, so when you think maximums, the first thing you should think is critical points. So here, if I take the derivative of my function, the derivative of 4,400Q is 4,400 minus, now the derivative of 10Q squared is 20Q, and the derivative of 1,400 is 0 because it's a constant. So for critical points, I want to know, when does that equal 0? So I would bring the 20Q over and then divide by 20 to solve for Q. So when I do that, I get Q equals 220. Okay, so that's my critical point. I want to make sure that this is actually a maximum, right? I don't want to accidentally minimize my profit. That would be really bad. So I'm going to use the second derivative test to make sure that this is a maximum. So the second derivative for my function, the derivative of 4,400 is 0, and the derivative of minus 20Q is minus 20. So here, the second derivative is negative 20. And we talked about this before, that if your second derivative is just a constant, you can still use it to classify your critical point, because that tells you the concavity everywhere. So if the second derivative is negative, your original function's concave down, which means that your critical point is a local max. So that's good. We've maximized our profit here. And so here the question is, what is the quantity? The quantity is 220. Now that's different than part E, which says, what is the maximum profit? So we know how many we have to make to maximize the profit, but what is the actual amount of money that we are going to bring in? So what we need to do is we need to take this value of 220 and we need to plug it back into the profit function to get that profit. So here, if we plug in a 220, I get 4,400 times 220 minus, and still using parentheses here, 10 times 220 squared plus 1,400. You're going to put that all into your calculator, and we are going to get, let's see, $482,600. Okay. So what I'm trying to emphasize here is that there's a difference between when we are asking what the quantity that maximizes profit is and what the actual maximum profit is. The quantity is the Q value, whereas the maximum profit is the actual amount from the profit function when you plug in the quantity that maximizes it. So pay special attention to the wording between these two. Okay, but again, when you see the word maximum or minimum in any context, the first thought you should have is critical points, right? Critical points help us find these maxes and mins. All right, so let's take a look at the next one. So here, this is just sort of a little conceptual idea of how all of these things are related. We did something similar to this back in chapter 2. But the question is, when profit is maximized, what is the relationship between the marginal cost and the marginal revenue? So we talked about this a little bit graphically. You may or may not remember, but I want you to think about a general profit function and what it means for that to be at a maximum. And then hopefully that'll help you remember the relationship between these two. And then for part B, if the marginal revenue at 45 is $57 and the marginal revenue at 45 items is $62, additionally, or approximately how much additional profit is earned by the 46th item? So this is just sort of to tie together the things we've been remembering about what derivatives tell us and how we use that to think about other applications. Okay, so take 2 minutes. Think about these two problems, think about how they're related, and see if you can figure these out, and then we'll go through them together. All right, take about 30 more seconds. All right, so for part A, we're talking about what happens when profit is maximized. So we think back to the general profit function. If we are maximizing profit, we are setting the derivative equal to 0. But the derivative of this function is going to be r prime of q minus e prime of q. And we want to know when that equals 0. We can write it this way because these were separated by subtraction, so we can take the derivative of each piece. So if the difference between these two are 0, that means that r prime of q has to be equal to c prime of q when we have a critical point. So the relationship between these two is that they are equal. Now we have to be a little careful here because they'll also be equal if we are minimizing, right, the profit, because This is just giving us critical points. But most of the time in business, right, the functions that we look at tend to be a parabola, right? That's just how that actually happens in the real world. And so we typically don't have a local minimum. We just have a local maximum. So most of the time, when you find these two things being equal, you are maximizing the profit. Okay, so for part B, this is just a reminder of what the derivative is telling us. And so the derivative is helping us remember that it's the change by adding one more item. So looking at one ahead, what's happening in the next one unit. So if we're talking about this function here, how much additional profit is earned by the 46th item? This question is really asking you for the marginal profit at 45, because when we talk about by the 46th item, we're talking about the difference in going from 45 to 46. And so sometimes we lose sight of the fact that the derivative is just talking about one unit away. So the marginal profit at 45 is the marginal revenue at quantity equals 45 minus the marginal cost at quantity equals 45. So the marginal revenue, let's see, is 62. The marginal cost is 57. So 62 minus 57 is going to give us a marginal profit of $5. So the additional profit to get to the 46th item is going to be $5. Okay, so this is just sort of a reminder about what derivatives tell us. So we're going to stop here for the day. We'll do some more of this next week, obviously. And just as a reminder, your quiz on Sunday is just about inflection points. This will be on next week's quiz. Okay, have a good weekend, and I will see you all on Tuesday.